This is lesson number 5, solving linear inequalities. In my opinion, linear inequalities are much more important than equations. In Algebra 1, you probably spent a lot more time solving equations than solving inequalities. Probably the reason for that is we need the notion of solving equations to solve inequalities. Why are inequalities more important? Because in the real world, they really are more meaningful. For example, a company has a budget. Let's say a budget for office supplies, and the budget is $500. Now, what does that mean? That means the company can spend any amount up to and including $500, but they cannot exceed $500. Inequalities are one of 4 types. We have a greater than. X is greater than 500, which means it must be a number to the right of the number line greater than 500. Or X could be greater than or equal to 500, which means it could be a larger number than 500 or equal to 500. X could be less than or equal to 500. That would be our budget situation where we could spend any number less than 500 or 500 itself. And then we could have X is strictly less than 500, where the number must be a number less than 500. Let's take an example of a typical inequality, and you'll notice how much like equations inequalities are. In fact, with one specific exception, we will solve inequalities the same way. Let's take a look at the first visual. We have an inequality 4x plus 3 is less than negative 5. You'll notice, as you can see the solution on the screen, that we've done the exact same thing we did in previous lessons in solving equations. That is, we subtracted 3 from both sides. Why? Because we wanted to isolate the variable expression 4x. We didn't want to know what 4x was less than. We wanted to know what x was less than. So we divided both sides by 4. X is less than negative 2. Now, we emphasized in previous lessons how important it is to check our work. How would you check that x is less than negative 2? Well, pick a number less than negative 2. For example, negative 3. Okay? And plug negative 3 into the original inequality. And you'd get negative 12 plus 3, which is negative 9, is less than negative 5. Less than, meaning to the left on the number line, negative 9 is less than negative 5, so it checks. You might also try a number that should not work. That is a number that's not less than negative 2. Let's see, let's try 0. 0 should not work. 4 times 0 is 0 plus 3 is 3. 3 is not less than negative 5. So therefore, a number that should work did, a number that should not work did not. Very important. Some difference there in checking because, remember, in inequality, there's not one answer. There's a whole smear of answers. All the numbers less than negative 2 will work. Negative 2.1, negative 3, negative 10 billion. All will be successful if you substitute that number into the original inequality. 4x plus 3 will be less than negative 5. Let's take a look at the next type of inequality, the next visual, which has 2 differences from the first inequality we looked at. The first difference is that x on both sides. The second difference is that it's greater than or equal to. The previous one was less than. Okay? Otherwise, we solve it the same way we solved equations in the past. What do? Well, we want to get rid of the 3x on the right side, so we subtract 3x from both sides. We want to get rid of the minus 7 on the left side, so we add 7 to both sides. We get 2x is greater than or equal to 8. We divide by 2, we get x is greater than or equal to 4. All numbers greater than or equal to 4. That means 4, because 4 is equal to 4, 4.01, 5, 6, 8, 12. Again, pick a number. As long as it's greater than or equal to 4, it should work in the original equation. In fact, I might suggest, when you have a chance, go back and check and make sure my answer is correct. I think you'll find it is. An important aspect of solving inequalities is being able to graph an inequality. And how we graph an inequality is using a number line. So first, let's go back, go to the board here, and look at what the number line looks like. The number line simply is a horizontal line that goes out in all directions, in both directions, infinite distance. Obviously, we don't have the time or the board space to go out infinite distance, so we have this arrowhead symbol in both directions, meaning it really is a line. It goes forever and ever. And someplace in the middle of that line we have 0. All numbers to the right of 0 are your positives. The further to the right you go, the larger the positive numbers become. Positive 1, 2, 7, 12, 4 billion. To the left are the negative numbers. Negative 1, negative 2. As we go further to the left, the numbers are more negative, but in terms of mathematical description, they are less, because less is to the left. A good way to remember that, in case you never could figure out what that meant, was think of temperature. Negative 6 is colder than negative 4. Yes, I know, they're both cold, but negative 6 is colder. It's further to the left, or on the thermometer, it's further down on the number line. So let's take a look at the first visual we have here on graphs. This is the graph of x is less than negative 2. Now, why is that familiar? Well, that was the solution to the first inequality we did. And notice we have drawn on the number line, we have negative 2 identified. There is a circle, it's called open circle, a non-filled in circle at negative 2, and an arrow going to the left. The arrow going to the left means less than. The open circle means not including negative 2. Because remember, the answer was x was less than negative 2. If I said to you, what was the largest number you can tell me that was less than negative 2? You might say, well, negative 2.1. Someone else over here might say negative 2.01. Someone else might say negative 2.001. And again, we'd be here forever, going to negative 2.000000. Uh-oh. Who wants to do that? So the idea is we never can get how close is close. We say simply that x is less than negative 2, so it can be as close as you want to negative 2 as long as it's not negative 2, and the symbol for that is that open circle. Let's take a look at the next visual. This is a graph of the solution to our second problem. X is greater than or equal to 4. Notice two things. The arrow goes to the right because it's greater than, and the circle is colored in, which means it includes the number 4. X is greater than or equal to 4. Now, I talked about checking, but I like to go back and emphasize it. And let's take a look at the next visual, which starts out with the same problem we had before. And that is the first problem, 4x plus 3 is less than negative 5. The solution was x is less than negative 2. And in this case, we tried x is equal to negative 3. Why do we try that? Because negative 3 is less than negative 2. It should work. It does. Notice the check mark. On the other hand, if we tried negative 2, it doesn't work. Because, now why doesn't it work? Because remember, x has to be less than negative 2, and negative 2 doesn't work. We could also try x equals negative 1. Now, if we try x equals negative 1, and this is shown on the visual, we plug in negative 1. 4 times negative 1 is negative 4, plus 3 is negative 1. Negative 1 is not less than negative 5. So we could check numbers that should work, numbers that should not work. I've said this twice on this tape because I think it's very important that you understand this. I can't emphasize enough how important it is to check your work. Obviously, when you're doing homework problems from a textbook, in many cases the answers are in the back of the book. But on a test or in the real world, the answers are not in the back of the book because there is no book. So checking is mighty important. Okay, another thing I mentioned earlier was that there is one very significant difference between solving equations and solving inequalities. And to demonstrate what I'm talking about, let's go back to our number line. Now, in fact, let me go ahead and widen this number line just a bit to make it possibly clearer for you. Here is the number A, and here is the number B. A and B are just numbers. This could be 1 and 2 or 3 and 7. We don't know what the scale of this board is. Would you say that A was less than B? Was A equal to B, or was A greater than B? I hope you'd say that A was less than B, because A is to the left. What if I multiplied both numbers by negative 2? Well, it might be over here. Here's negative 2A, and here's negative 2B. Now, if I wrote negative 2A and negative 2B, what symbol would you put in between? Would you still put less than? And the answer, I think, is no, because you'll notice that negative 2a is to the right of negative 2b. You'd put greater than. This is the one difference. When you multiply or divide both sides of an inequality by a negative, it changes the direction of the inequality. You may have heard that in Algebra 1, and if you're already taking Algebra 2, you may have heard that, and it was just like, this was a rule that came down from the mountaintop. You know, there was a bolt of lightning, and they said, when you multiply or divide both sides of an inequality by a negative, you change the direction of inequality. There is a reason for everything in mathematics, and a very good reason here is demonstrated. When you multiply by a negative, notice what happens. The positive numbers both become negative. The number that was closer to 0, a, is still closer to 0, negative 2a. The number that was further from 0 is still further from 0. But now the number that was closer to 0 is to the right. Before it was to the left. Since it's to the right of the other number, it's greater than. Before it was to the left and it was less than. That is, when you multiply by a negative, the numbers maintain their relative position from 0. In other words, the number that was further from 0 stays further from 0. But instead of being further to the right, it's further to the left. Further to the right means greater than. Further to the left means less than. And therefore, the rule that you should remember, but now you know why it works, is that if you multiply both sides of an inequality by a negative, you must change the direction of the inequality. Less than becomes greater than, less than or equal to becomes greater than or equal to, and vice versa. So let's take a look at the next visual. The next visual has an inequality, 4 minus 2x is less than or equal to 6. We start off the same way as we did with other inequalities and equations. We subtract the 4 to isolate the negative 2x. Negative 2x is less than or equal to 2. We divide both sides by a negative 2. We are dividing by a negative. So x becomes greater than or equal to negative 1. The next thing we want to discuss is compound inequalities. What does compound mean? Compound means complex, more than one thing. These are inequalities that have more than one inequality in them. Excuse me a second. And for those who are worried, that's just water. We have the next visual, which is a compound inequality. That is, 2x plus 3 can be greater than 9, or x minus 2 is less than negative 1. Okay? What we simply do is solve the two inequalities independently, leaving that word or between the two solutions. We divide by 2, and the 2x is greater than 6. We divide, we don't have to divide when x is less than 1. So we get x is greater than 3, or x is less than 1. And you can see the graph. Why are there open circles in the graph? Because x must be less than 1. If x was less than or equal to 1, then the circle, we call it in. X is greater than 3. So that, again, the circle is open. Since it's greater than 3, the arrow goes to the right, coming out of the 3. Since its x is less than 1, the arrow coming out of the circle at the 1 is to the left. So this is a complete solution. That is, we solve each part of the compound inequality independently, leaving the word or, in this case, in between. Our solution has two parts with the word or in between. And what does or mean? It means one or the other. So our graph is one goes this way, one goes that way. And therefore, for example, if we were going to check this problem, let's go back to that same visual with the graph. Concentrate on looking at the graph. What would a number work? Well, a number would work anything greater than 3. So we try 4. 4 should work. Another number that could work would be a number less than 1. We could try 0. And how about a number that would not work? Well, any number in that gap between 1 and 3, for example, 2, would not work. So therefore, if we tried 4, it should work. If we tried 0, it should work. If we tried 2, it should not work. And by doing this checking, we again make sure that we see our answer is correct. And again, it's a compound answer, has two parts, because this was a compound inequality. Another type of compound inequality is demonstrated in the next visual. This is one, there's no word or here. This is sort of what's called a between That is, the 2x minus 8, the variable part of our inequality, is between -4 and 10. Look carefully at that compound inequality, the first line. You'll notice that if you go from left to right, -4 is less than or equal to something, some number, 2x minus 8, which is less than 10. It flows from left to right. That is, -4 ultimately is less than 10. You'll notice both inequalities are going in the same direction, although one is less than or equal to and one is purely less than. The solutions are indicated. Again, we treat the 2x minus 8 as being part of two different inequalities, and independently of each other, we go ahead and solve. We solve -4 is less than or equal to 2x minus 8. We solve 2x minus 8 is less than 10. The solution is no different than anything we've done before, although you'll notice on the left-hand side we wind up with the x on the right. That is, our solution is 2 is less than or equal to x. The other solution is x is less than 9. Again, a compound inequality must have a compound solution. So looking at the last line in the solution, we see that the answer is 2 is less than or equal to x is less than 9. And notice that 2 indeed is less than 9. That is, another way of saying this is that x is between 2 and 9, including 2. Why including 2? Because 2 is less than or equal to x. So 2 could be x. X could also be 3 or 4 or 4.2 or 5.7 or 8.99. X cannot be 9. And if you look at the graph, it's very clear what x could be. Notice there are no arrows on our solution. It starts at 2 with a colored-in circle, and then we've colored in the area, the line part, between 2 and 9 has an open circle. Why? Because the answer is 2 is less than or equal to x, which is less than 9. So all the numbers between 2 and 9, not including 9, but including 2, will work. Now, we've already looked at absolute value equations. We saw those. Well, let's take a look at absolute value inequalities. My experience over the years of teaching has been that students tend to have difficulty with this. And the reason, I believe, is because they haven't figured out what absolute value inequalities mean. So let's go back to our definition of absolute value. Absolute value was the distance from 0. If you can remember that, then an absolute value inequality makes a great deal of sense. Let's take a look at an absolute value inequality at the board here. We go ahead and erase our number line. And again, if you feel the need to use that number line, rewind the tape, go back to it, look at it again. And the problem we're going to look at is 2x minus 3 is greater than 7. Certainly makes a difference whether it's less than or greater than. Now, before we go to our solution, I want you to look at this and see what it means. Think about what this says. What this says to me is that I have some number. Remember, 2x minus 3 is a number. We just don't know what x is, and therefore we do not know what 2x minus 3 is. This number is absolute value greater than 7. What does that mean? Well, let's assume this number was a positive number. That is, it's on the right side of 0. It's the distance away from 0, this number is greater than 7 units. Well, to be a positive number and be further away than 7, one must be to the right of 7. It's all the numbers out here, 7.1, 8, 10, 12, 400,000. But what if 2x minus 3 was negative? If it was negative, well, that would mean we have a negative number that's further away from 0 than 7 is. Well, negative 7 is 7 away from 0, and this number has to be further away, so it has to be beyond negative 7. So we can really see we have two solutions. We're back to a compound inequality. 2x minus 3 is either greater than 7, out here, or 2x minus 3 is less than negative 7, out here. The word or. One way I try to get my students to remember this is think of the absolute value symbol as two walls. Greater than means you're outside the walls. You're either outside up here or outside down there. It's an or situation. If you think about it, you can't be both places. I mean, a person couldn't be on this side of the wall and on that side of that wall at the same time. It's impossible. So therefore, it's an or situation. You're either here or you're there. Remembering that, we can look at the visual. Because in the visual, what we have is the solution. Again, recognizing what the inequality means, we write the compound inequality. 2x minus 3 is greater than 7, or 2x minus 3 is less than negative 7. We solve independently the two inequalities, leaving the word or in between, and come up with x is greater than 5, or x is less than negative 2. And again, we check by picking numbers that were greater than 5, a number less than negative 2, and then finding a number that was not. For example, how about the 0? 0 is not greater than 5, 0 is not less than negative 2, and 0 should not work. Again, the difference between solving equations, we check the answers, and solving inequalities, we check numbers that should work and numbers that should not work. Let's take a look at the next inequality, which is the next visual. What is the difference between this inequality and the previous one? There are two differences. One is it's less than, as opposed to greater than, and it's less than or equal to. Now, what does that mean? Again, this means that the 5x minus 10 is closer to 0 than 15, or is the same distance. And I like to look at it, going back to my walls, that if you're less than, if your absolute value is less than, it means you're inside the walls. In fact, let's go to the board and take a look at what that inequality would look like, and then we'll go back to the visual to take a look at the solution again. 5x minus 10, absolute value, is less than or equal to 15. Again, the way I look at that is you are closer than the walls, which means you've got to be inside the walls. That is, you've got to be less than inside this wall and greater than inside this wall. So we're going to wind up with an in-between solution, like we had in a previous compound inequality. We should wind up with an answer that something is less than x, or less than or equal to x, which is less than or equal to another number. So let's go back to the visual that gives us the solution to this inequality. Again, we write the word and, because you must be both inside one wall and inside the other wall. What do we see? We solve the inequalities. We wind up with x is less than 5 and x is greater than negative 1. We have to ask ourselves the question, can you find a number that is less than or equal to 5 and greater than or equal to negative 1? And the answer is, of course, you can. Negative 1 is greater than or equal to negative 1 and less than 5. 0, 1, 2, 3, 4, up to 5. So all the numbers from negative 1 through 5, including negative 1 and 5. And again, the negative 1 and 5 are included because of the equals, less than or equals in the original problem. What do we have? We have our solution. Negative 1 is less than or equal to x, which is less than or equal to 5. Remember what I said. When you read one of these from left to right, it should flow. Negative 1 is less than or equal to 5. And x is between those two numbers. So again, in our checking, we could check 0, certainly as an interval. We could check a number that would not work. Think of a number that would not work. Hopefully you thought of a number like 6 or 7, which of course is not less than or equal to 5, or perhaps a number like negative 2 or negative 3, which is not greater than or equal to negative 1. And it should check. And again, I'll leave that checking up to you. You can stop the tape if you like and go ahead and check. Or we can go on to look at an alternate method. That is another method of solving these inequalities. As I think I've mentioned before, I don't believe that there's only one right way of doing something. And if you don't like this method with the walls, let me show you another method. So let's go to the next visual, which shows us an inequality, 3x plus 7 less than negative 5x minus 9. And it has the words solve equation. What does that mean? It means simply change the inequality into an equation, which I've done. 3x plus 7 equals negative 5x minus 9. We know how to solve this. The steps, we get x equals negative 2. Now, what does that mean? It means that when x equals negative 2, the equation has a solution. But we want a situation where one side is less than, not equal to the other side. So all we do is then we test points. So let's look at the next visual, which has our inequality. 3x plus 7 is less than negative 5x minus 9. And the words test points. Test points on the number line. For example, x equals negative 3. Well, negative 3 is less than negative 2. So if negative 3 works, that would mean that x would be less than negative 2. And we plug in negative 3 and we get that negative 2 is less than 6. The check mark indicates that negative 3 works, which means certainly any number to the left of negative 2, less than negative 2, should work. And we try a number on the other side. We try negative 1, because negative 1, of course, is greater than negative 2. This would test the solution x is greater than negative 2. You may say, why don't we just stop since we know x is less than negative 2? Oh, no. It's a good idea to check both sides to make sure you didn't mess up in your first part. And we plug in negative 1 into the inequality, and we get 4 is less than negative 4. This is not correct. This is not an answer. 4 is not less than negative 4. And therefore, if we go back to the next visual, we can see again the original inequality. And it says, and this is important to remember, negative 3 worked and negative 1 did not. And again, our key thing was we had to work around the solution to the equation x equals negative 2. And therefore, x is less than negative 2 is the solution. I'll be quite frank with you. I like the first method better. But I have seen teachers who like to use the equation and then test points situation. And if that makes sense to you, or if that's what your teacher is using, there's a good example. But I'd like to go back now and review what we've done in this lesson. Because to me, solving inequalities again is very, very important. It really comes important in applications in later mathematics, and even including in business courses and science courses, where you're dealing with the real world, where you have up to and including, or up to but not including, but certainly not beyond some things. For example, if any of you are applying to get into a military academy, the military academies have height requirements. They're different for males and females. And it's in between. You must be taller than a certain minimum height and shorter than a maximal height. And some people might ask how David Robinson ever got into the Naval Academy. That's because he grew a number of inches while he was in the Naval Academy. Had he been as tall when he applied as he is now, he would never have been admitted, because his height right now is taller than the maximal height of the inequality that's established for entrance into the U.S. Naval Academy. The first thing to remember is that solving an inequality is no different than solving an equation, with one exception. And that one exception is that when you multiply or divide both sides of the inequality by a negative, you change the direction of inequality. Less than becomes greater than becomes less than or equal to becomes greater than or equal to, etc. And the reason for this, if you've forgotten, rewind the tape. I think I've explained it fairly clearly. Otherwise, we simply solve as we did before. We isolate the variable, divide to get rid of multiplication. But remember, if you divide by a negative, you've got to change the direction of inequality. And then, instead of checking by looking at one solution or two solutions, as we saw in some equations, we test values. Values that should work, values that should not work in the original inequality. And the graphing of inequalities is important, because in equations, we have only one solution, x equals 7. Here, if we have x is less than 3, visualizing it is very helpful. So it's all the numbers to the left of 3, and we use the graphing techniques of using the number line. The open circle, the non-colored in circle, meaning less than or equal to or greater than or equal to. That is not including that number. The colored in circle means including that number. If a solution is greater than, for example, x is greater than 5, we'd have a circle, an open circle around 5, and a line with an arrow going to the right, indicating greater than. To the left, we have a line with an arrow indicating less than. This ends our solving linear inequalities, and we go on in the next lesson to looking at the line and the use of the line in correlation of real-world events.